You have probably seen Europa without knowing it. It is one of the small points of light beside Jupiter, a pale cream-coloured marble that Galileo Galilei first noticed in 1610. From far away it looks calm, almost polished, the smoothest large surface in the whole solar system. Tonight we're going to Europa, and to something the James Webb Space Telescope found there in 2023. The word that travelled afterward was panic. The truth was quieter and stranger. Webb saw carbon dioxide frozen on the ice, and the carbon did not seem to have fallen from space. It seemed to have risen from an ocean hidden under the crust. That one fact turned a frozen moon into one of the best places we have to ask whether we are alone. So let us slow down and look at what is really down there. Picture a ball of ice about the size of our own moon, hanging in the black beside Jupiter. That is Europa. From a distance, it is one of the palest things you could point a telescope at, a soft cream colour crossed by faint reddish lines. What stands out most is how smooth it looks. If you could shrink Europa to the size of a billiard ball, it would come out smoother than the billiard ball. Across the whole world there are almost no tall mountains and almost no deep canyons. The highest ridges rise only a few hundred feet, low enough that you could walk over most of them and barely notice the climb. That smoothness is strange, and it is the first clue in this story. Nearly every other solid world we know is battered. Our moon is covered in craters, some older than the first life on Earth, each one a scar from a rock that fell out of the sky and was never erased. Mercury is the same, so are the icy moons of Saturn. A surface collects craters the way an old table collects scratches, and the more scratches you count, the older the surface must be. By that simple logic, Europa should be pockmarked from pole to pole. It has orbited inside the busy rocky neighbourhood of Jupiter for billions of years, and Jupiter's gravity actually pulls extra debris inward, so Europa has been shot at more than most. Yet when you look, the scars are missing. Astronomers have searched the best images we have, and across an entire moon they can find only a small handful of large craters. You could count the obvious ones on your fingers. For a surface that has sat out in the open for 4.5 billion years, that should be impossible. Something has been wiping Europa clean. That single fact reshapes everything. A smooth face means a young face. Whatever we're looking at is not the ancient original crust of the moon. It is a fresh coat, laid down long after Europa formed, and it is still being renewed. The old scars are gone because the surface itself keeps getting replaced, and a surface that renews itself has to be fed by something underneath, some source of new material and new energy that reaches up from below and smooths the world over again and again. So the pale, quiet marble is not quiet at all. It only looks that way from far off, the way a frozen lake looks still on a winter morning, even while water moves beneath the ice. Europa is a world with a lid, and the lid is thin enough and young enough that whatever lives under it keeps leaving traces on top. Everything else in this story grows from that one observation. The carbon that the James Webb Space Telescope would find, the salts, the strange chemistry, the reason anyone cares about this moon at all begins here, with a surface too smooth to be as old as it is. To understand how we learned all of this, and how a smudge of light became one of the most promising places in the solar system, we have to go back to the person who first saw Europa at all. He did not see a marble, or an ocean, or anything but a faint spark that moved. He saw 4 sparks, in fact, and the way they moved changed how human beings understood their place in the universe. Those 4 points of light are where the real story begins. On a January night in 1610, an Italian astronomer named Galileo Galilei pointed a small handmade telescope at Jupiter. The instrument was crude by any modern standard, barely stronger than a pair of cheap binoculars. Through it, Jupiter showed as a small bright disk, but strung out in a line beside the planet were 3 little stars he had never noticed before. He drew them. The next night he looked again, and the stars had moved. Over the following nights a 4th appeared, and all of them shifted back and forth, sometimes vanishing behind the planet, always staying close to it. Ordinary stars do not do this. Galileo understood what he was seeing. These were not stars at all. They were worlds, 4 moons circling Jupiter the way our moon circles Earth. It was the first time anyone had watched objects clearly orbiting something other than our own planet, and it quietly demolished the old idea that everything in the heavens turned around us. The 4 moons are now called the Galilean moons in his honour. From Jupiter outward they are Io, Europa, Ganymede, and Callisto. If you find these slow journeys through the solar system worth returning to, you are welcome to subscribe and take the next one with me. Europa is the second of the 4 and the smallest of them. It is a little smaller than our own moon, so if you set the 2 side by side, Europa would look like a slightly shrunken, brighter version. Io, the innermost, is a hellscape of volcanoes. Ganymede, the third, is the largest moon in the entire solar system, bigger even than the planet Mercury. Callisto, the outermost, is an ancient, cratered relic. Among these very different siblings, Europa is the pale, smooth one, and for centuries it was little more than a point of light that got brighter as our telescopes improved. For more than 350 years, that is all Europa was, a dot. Astronomers measured how long it took to circle Jupiter, a little over 3.5 days, and they tracked its brightness, but they could not see its face. It was too far away and too small. Even in the finest observatories, Europa stayed a featureless speck against the glare of the giant planet next to it. Everything we now know about the surface, the cracks, the smoothness, the chemistry, came only when we stopped looking from Earth and started sending machines to fly past. The dot had to become a place, and when the first spacecraft finally reached Jupiter and turned their cameras toward this particular moon, what came back did not look like a dead ball of rock and ice. It looked like something that had been alive with movement, a surface written all over with lines, as if a child had scribbled across it in reddish-brown crayon, and then someone had tried, not quite successfully, to erase it. Those lines were the next great puzzle. They cover Europa from end to end, thousands of miles long, crossing and recrossing each other in a tangle that no dead world should have. Before we can talk about oceans or carbon, or the search for life, we have to understand those marks, because they are the surface's own record of what has been happening to it. And to read them, we first had to explain the thing we already noticed from a distance. We had to explain why a world this old could look this new. Count the craters on any surface in the solar system and you are really counting time. Every world sits in a slow, endless rain of debris, chunks of rock and ice left over from the building of the planets. Each impact leaves a bowl. The bowls pile up. So a heavily cratered surface, like our moon or like Mercury, is an old surface, one that has been collecting hits for billions of years without anything to smooth them away. This is one of the most reliable clocks planetary scientists have. More craters means more age. By that clock, Europa reads as almost brand new. When spacecraft finally photographed it up close, scientists went looking for the expected billions of years of scars and could not find them. Across the whole moon, only a few large impact craters stand out clearly. The most famous of them, a formation named Puil, has bright rays of fresh material splashed out around it, the mark of a relatively recent hit. Fresh craters like that stand out precisely because they have so little company. On a truly ancient surface, new craters would be lost in a crowd of old ones. On Europa, they sit almost alone. When you turn that crater count into an age, you get a number that seems too small to be real. The visible surface of Europa may be only tens of millions of years old. Set against the 4.5 billion years the solar system has existed, that is the blink of an eye. It would be as if you found a house that was built when the dinosaurs still ruled, and discovered that every wall had been repainted sometime in the last few weeks. The building is ancient. The paint is new. Something has been resurfacing Europa, erasing its craters roughly as fast as they form. And that raises an obvious problem, because erasing craters takes energy. On Earth, our surface renews itself through moving continents, erupting volcanoes, wind and flowing water, all powered ultimately by the heat of a large warm planet. Europa is small. A small world should have cooled off and gone still long ago, the way a small cup of coffee goes cold faster than a large pot. Little Europa, by every reasonable expectation, should be a frozen, dead, cratered ball like its neighbour Callisto. It is not. It is smooth and young and clearly active, so there must be a source of heat and motion hiding inside it, strong enough to keep remaking the whole surface, and that heat has to come from somewhere other than leftover warmth from its birth. Finding that hidden furnace is one of the keys to the entire mystery, and we will come to it. For now, hold on to the strangeness of the fact itself. A world that should be dead is behaving like a world that is alive. The resurfacing also does something helpful for us. If the crust is being renewed from below, then material from deep inside Europa is being carried up and spread across the top. The surface becomes a kind of message board, posting samples of whatever lies beneath. That is exactly why a telescope looking only at the outside of Europa could, in principle, learn something about what is hidden inside it. The smoothness that first puzzled us turns out to be an invitation. It tells us the inside and the outside are connected, and the clearest sign of that connection is written across the surface in long, dark, reddish lines. They are the next thing to understand, because those lines are the seams where the crust has cracked open, and what fills them did not come from space. It welled up from below. The most striking thing about Europa up close is not the smoothness. It is the lines. The entire moon is wrapped in them, long dark streaks that run for hundreds and even thousands of miles, curving gently across the ice and crossing over one another again and again. Scientists call them lineae, which is simply the Latin word for lines. Some are single cracks. Others are broad bands, wide as a highway is long, with a pale stripe running down the centre and darker edges to either side. Seen all together, they make Europa look like a cracked eggshell, or like a ball of string that has been wound and rewound until the surface is nothing but overlapping threads. These lines are cracks in the ice, and they tell us the crust is being pulled and pushed hard enough to split. On a dead, frozen world, ice just sits there. On Europa, the ice is breaking on a global scale over and over, in patterns that record different episodes of stress stacked on top of each other. When scientists trace the youngest cracks over the oldest, they can read the order of events, the way you can tell which pencil mark was drawn last when two of them cross. What fills the cracks is the real prize. The lines are not white like the surrounding ice. They are reddish-brown, a dirty rust colour, and that colour is a chemical fingerprint. When fresh material rises into an open crack from below and freezes at the surface, it gets blasted by radiation from Jupiter, and that bombardment darkens and reddens certain compounds. So the colour is telling us two things at once. It is telling us that stuff is coming up from inside, and it is telling us that whatever comes up is being chemically altered once it arrives. For a long time, no one knew exactly what the reddish material was. The leading idea was salt, ordinary and not so ordinary salts carried up from a hidden interior. Later work with the Hubble Space Telescope found evidence for sodium chloride, the same table salt you keep in your kitchen, concentrated in certain regions of the surface. Salt at the surface strongly suggests salt water down below, because salt does not simply appear on a frozen moon. It has to be dissolved in something and then carried up. Think about what that means. If the dark lines are cracks, and the cracks are filled with material that welled up from inside, and that material carries salt, then whatever lies beneath the ice is not solid rock. It is something that can dissolve minerals and flow into the openings when the crust splits. It behaves like a liquid. It behaves, in fact, like an ocean. The lines also tell us the ice moves. In places you can see where a band of crust has clearly slid sideways, or where two edges that once fit together have been pulled apart, leaving a gap that filled in with fresher, smoother ice. This is the surface caught in the act of spreading, a little like the way the seafloor spreads here on Earth, except made of ice rather than stone. The lid over Europa is not a single frozen sheet. It is a shifting, cracking shell riding on top of something that yields, so the linear carry us one step deeper. The smoothness told us the surface was young and renewed. The lines tell us how that renewal happens, through cracking and refilling from below, and they hint at what does the refilling. But cracks are only the gentlest sign of what is happening to this crust. In some places, the surface has not merely split, it has completely broken apart, shattered into rafts of ice that drifted, tilted, and froze back into place like puzzle pieces jammed into the wrong slots. Those wrecked regions have a name, and they may be the closest thing we have to a window straight down toward the sea. In some parts of Europa, the neat pattern of lines gives way to something that looks like a disaster. The smooth ice is shattered. Great blocks of crust, some of them miles across, sit tilted and rotated, shoved together at odd angles, with rougher frozen material filling the gaps between them. It looks exactly like what you would see if a frozen lake broke up in a spring thaw, drifted apart into floating rafts, and then froze solid again before the pieces could settle back into place. Scientists call these wrecked regions chaos terrain, and the name fits. Chaos terrain is one of the most important things on Europa because of what it seems to require. To break the ice into rafts and let them drift, you need the ice to stop being rigid, at least for a while, at least underneath. You need something soft or liquid below to float the blocks on. The most natural explanation is that in these places the warm interior came close to the surface, weakened or melted the base of the ice, and let the top break up and shuffle around before refreezing. In other words, chaos terrain may be where the hidden ocean, or pockets of it, pushed nearest to the top. That makes these regions the best natural sampling sites on the whole moon. If material from deep inside Europa ever reaches the surface in bulk, chaos terrain is where you would expect to find it, freshly delivered and not yet buried. Any chemistry from below, any salt, any carbon, any hint of the ocean's makeup should be concentrated in these broken zones. Keep that idea close, because it becomes the hinge of the entire story. When the James Webb Space Telescope eventually found carbon on Europa, it did not find it spread evenly. It found it piled up in exactly this kind of terrain. One chaos region in particular will matter to us more than any other. It is a yellowish, mottled patch to one side of Europa's centre, and it carries the name Tara Regio. It is a place where the surface has plainly been torn up and put back together, and it is where, years before Webb, the Hubble Space Telescope had already spotted signs of ocean salt. For now, simply file the name away. Tara Regio is the address we will keep returning to. There is real debate about how chaos terrain forms, and it is worth being honest that the picture is not settled. Some scientists think large lakes of liquid water form within the ice shell itself, well above the main ocean, and that these shallow lakes crack the surface from below without the deep ocean ever touching the top. Others think the connection runs all the way down to the sea. The distinction sounds technical, but it goes to the heart of the question that drives Europa research, which is how much the surface and the ocean actually talk to each other. If they trade material freely, then the top of Europa is a readable record of the sea. If they barely connect, then the surface keeps the ocean's secrets. Either way, chaos terrain proves that Europa's crust has been mobile, warm and broken. Not once, but many times, in many places. This is not the behaviour of a frozen relic. It is the behaviour of a shell floating on something that moves. And that brings us to the thing under the ice. The possibility that had been growing in the minds of scientists with every new observation. The smoothness, the youth, the salt-stained cracks, the shattered and refrozen rafts, all of it pointed the same direction, downward toward liquid water. But pointing toward an ocean is not the same as proving one is there. To go from a strong suspicion to something close to certainty took a very different kind of clue, and a spacecraft that spent years circling Jupiter to find it. By the middle of the 20th century, a few scientists were willing to say something that sounded like science fiction. Beneath the ice of Europa, they suggested, there might be an ocean of liquid water. The reasoning was indirect but sound. The surface was clearly water ice. The surface was clearly young and active. Something warm had to be driving that activity. And if you warm water ice enough, you get water. The cracks and the salts all fit. Still, it remained an educated guess, the kind of idea that's easy to propose and hard to confirm from hundreds of millions of miles away. The problem is that an ocean under many miles of ice is almost perfectly hidden. You cannot see it. Light does not reach it and does not come back out. You cannot easily hear it. From the outside, a moon with a buried ocean and a moon that is frozen solid all the way through can look nearly the same. To tell them apart, you need a clue that can pass through solid ice and carry information about what lies beneath. For a long time, no one was sure such a clue existed. The first real look came from far away when the two Voyager spacecraft flew through the Jupiter system in 1979. Their cameras were the ones that first revealed the cracked, streaked surface, turning Europa from a dot into a place. The images were enough to make the ocean idea respectable and to make Europa a target worth returning to. But a fast flyby cannot linger. Voyager saw the surface and moved on, leaving the deeper question open. Was the water real, and was it there now, or had it frozen away ages ago? To answer that, you needed a spacecraft that would stay. In 1995, one arrived. A NASA probe named after Galileo Galilei himself settled into orbit around Jupiter and spent the next 8 years looping through the giant planet's family of moons, passing Europa again and again. Where Voyager had glimpsed, Galileo studied. It mapped the chaos terrain in detail, it measured the ice, and carried among its instruments was one device that would, almost by accident, turn the ocean from a guess into something very close to a fact. That instrument did not take pictures at all. It measured magnetism. And to understand why a magnetometer of all things became the tool that revealed a hidden sea, you have to understand the peculiar situation Europa sits in. It orbits deep inside the enormous magnetic field of Jupiter, the largest magnetic field of any planet in the solar system, a field so strong and so tilted that as Jupiter rotates, it sweeps past Europa and washes over the moon from constantly changing directions. Europa is bathed in a magnetic environment that never holds still. That turns out to matter enormously. When a changing magnetic field passes through a material that can conduct electricity, it stirs up electric currents inside that material, and those currents create a magnetic field of their own that pushes back. It is the same basic physics that runs the electric motors and generators in everyday life. Salt water is a good conductor. Pure ice and dry rock are not. So if Europa had a layer of salty liquid water inside it, Jupiter's restless field would induce currents in that layer, and the ocean would answer back with a faint magnetic signal of its own, a signal shaped in a very particular telltale way. All the Galileo spacecraft had to do was fly close enough to feel it. Whether Europa carried that hidden magnetic echo or stayed silent like a frozen stone would decide the question. And what the magnetometer detected, pass after pass, is where the ocean stopped being a dream and became a measurement. Each time the Galileo spacecraft swung close to Europa, its magnetometer read the magnetic field around the moon. If Europa were a dead, dry ball, the only field it should show is Jupiter's, passing through untouched. Instead, the instrument found something extra. There was an added magnetic field coming from Europa itself, and it was not the steady kind you would get from a permanent magnet buried in the core. It was the responsive kind, the sort that appears only when currents are being stirred up by the changing field around it, and it shifted exactly in step with Jupiter's sweeping magnetism. This is called an induced magnetic field, and it was the clue scientists had hardly dared hope for. Europa was answering Jupiter. Something inside the moon was conducting electricity well enough to generate its own magnetic echo, and it was doing so from a shell not far below the surface. The measurements pointed to a layer, tens of miles thick, wrapped around the moon, made of a material that carries current the way salty water does. Pure ice could not do it. A global ocean of salty liquid water could, almost perfectly. The strength and the timing of the response even hinted at how salty and how deep the layer had to be. To match what Galileo measured, Europa needed a substantial ocean, not a few isolated pockets, but a continuous conducting shell surrounding the whole moon beneath the ice. It was as close to direct evidence of a global subsurface ocean as you can get without drilling. The water itself stayed invisible, but its electrical shadow was unmistakable. It is worth sitting with how elegant this is. We confirmed an ocean we cannot see, on a moon we have never landed on, by measuring how it disturbed the magnetic field of the planet it orbits. No camera could have done it. The ocean gave itself away not through light, but through the way it conducts electricity, a property you would never guess by looking. Sometimes the most hidden things announce themselves in the most roundabout ways, and a scientist willing to measure the right quantity can hear them. With the magnetic evidence in hand, the picture of Europa snapped into focus. Beneath a shell of water ice lies a global ocean of salty liquid water, kept liquid somehow, resting on a floor of rock. The smooth surface, the young age, the cracks stained with salt, the shattered chaos terrain, all of it now had a foundation. These were the surface expressions of a living, moving ocean underneath, an ocean that occasionally cracks its lid, floats its ice into rafts, and leaves its salts on top for us to find. That single conclusion is why Europa matters so much. Liquid water is the one ingredient that every form of life we know of absolutely requires. We can imagine strange chemistries and exotic conditions, but so far every living thing we have ever studied, without exception, needs liquid water at its core. And here, on a small moon of Jupiter, is not a puddle but an entire sea, possibly holding more water than every ocean on Earth combined. It has likely been there, dark and undisturbed, for billions of years. But an ocean by itself is not enough. A sea can be sterile. To even ask whether Europa could host life, we need to understand three things about that ocean, and the first of them is the one that seems most impossible for a small, cold moon so far from the sun. The ocean has to stay liquid. Water does not remain liquid on its own out there in the deep cold of the outer solar system. Something has to be heating it, steadily, for billions of years. And the source of that heat is not the sun at all. It is the relentless grip of Jupiter and the strange dance Europa performs with its sister moons. Out at Jupiter, sunlight is weak. The giant planet orbits more than 5 times farther from the sun than Earth does, and sunlight fades fast with distance, so Europa receives only a small fraction of the warmth we get. At the surface, temperatures hover somewhere around -160 degrees Celsius, cold enough that water ice there is as hard as rock. By every expectation from sunlight alone, Europa's ocean should have frozen solid to the seafloor long ago. Something else is keeping it warm from within, and that something is not leftover heat and not sunlight. It is motion, forced on Europa by gravity. Europa does not orbit Jupiter alone. It is caught in a precise rhythm with 2 of its sister moons, Io on the inside and Ganymede on the outside. For every 4 times Io circles Jupiter, Europa goes around twice, and Ganymede goes around once. This locked, whole number pattern is called an orbital resonance, and it was worked out in its details by the mathematician Pierre-Simon Laplace, so it is often named the Laplace resonance in his honour. The 3 moons meet up in the same arrangement over and over, and each time they do, they tug on one another gravitationally, always in the same direction. Those repeated tugs matter because they keep Europa's orbit from becoming a perfect circle. Left alone, an orbit tends to relax into a circle, but the steady pulling from Io and Ganymede keeps stretching Europa's path into a slight oval. That small imperfection is the whole secret. As Europa travels along an oval orbit, it moves closer to Jupiter and then farther away again and again every trip around. And Jupiter's gravity is so immense that the difference in pull between the near side and the far side of Europa actually flexes the moon. Think of squeezing a rubber ball in your hand, over and over. The rubber warms up. Bend a paperclip back and forth quickly, and the metal at the bend grows hot. Europa is being kneaded in just this way by the changing grip of Jupiter. its entire body rising and falling by tens of feet as it swings through each orbit, a little over 3.5 days long. All that constant flexing generates heat deep inside, through friction in the rock and the ice. This is called tidal heating, and it is the furnace that has kept Europa's ocean liquid for billions of years. You can see the same engine running far more violently on Europa's neighbour Io. Io sits closer to Jupiter and gets flexed even harder, so hard that its interior is partly molten, and its surface erupts with hundreds of volcanoes, making it the most volcanically active world in the solar system. Europa feels a gentler version of the same squeeze. Not enough to melt rock into lava, but more than enough to melt ice into a sea and to keep it from freezing back. The same gravitational dance that turns Io into a furnace turns Europa into a warm, wet world under a frozen roof. This is a genuinely new way to think about where life might live. For a long time we imagined that a world had to sit at just the right distance from its star, close enough to be warm and far enough not to boil, in a narrow band we call the habitable zone. Europa is nowhere near that band. It is out in the cold, and by the old rule it should be lifeless. Yet it may hold a warm ocean anyway, heated not by a star but by gravity and rhythm. If that is possible here, it is possible around countless other worlds, and the places where life could exist suddenly multiply. So the ocean is real, and it is warm. The next question is the size of the roof above it. How thick is the ice between that hidden sea and the surface we can see? The answer, it turns out, is one of the most stubbornly uncertain numbers in all of Europa science. Everything about Europa's promise, and everything about how hard it is to explore, comes down to one measurement we still cannot pin down. How thick is the ice? Between the surface we can photograph and the ocean we have detected, there lies a shell of solid water ice, and its thickness matters enormously. A thin shell would mean the ocean is close, easier to sample, more likely to be trading material with the surface. A thick shell would seal the sea away, keeping its chemistry to itself. The honest answer, even now, is that we are not sure, and the range of possibilities is wide. Estimates run from as little as a few miles to more than 20 miles of ice. That is an enormous spread. It is the difference between a frozen pond you might one day drill through and a glacier deeper than the tallest mountains on Earth are high. Different lines of evidence pull in different directions, and each depends on assumptions we cannot yet check directly. This is one of those places where it is better to say plainly that we do not know than to pretend the matter is settled. The disagreement is not sloppiness. It comes from the fact that we are reading the thickness indirectly, from surface features, and those features can be explained in more than one way. Take the chaos terrain, the shattered regions we looked at earlier. If those form because the deep ocean pushes right up against the base of a thin shell, that argues for ice only a few miles thick. But if they form instead from shallow lakes of melt trapped within a much thicker shell, well above the true ocean, then the ice could be many times deeper and the ocean far out of reach. The same broken landscape supports two very different pictures. Other clues add their own hints without resolving the argument. The way heat flows out of Europa, the size and spacing of certain ridges, the gentle sag of the crust in places, each can be turned into an ice thickness, and each comes with its own uncertainty. Some studies favour a thinner shell, perhaps only a few miles in spots. Others favour a thick one, 20 miles or more. It is even possible that both are right in different places, that the ice varies from region to region, thinner over the warm chaos zones and thicker elsewhere, like a frozen lake that is solid in the middle and dangerously thin near a spring. This uncertainty is exactly why a telescope became so valuable. If you cannot yet drill through the ice, and you cannot yet fly a spacecraft close enough to peer beneath it, then you look at what the surface can tell you from a distance. And the single most useful thing the surface can offer is a sample of the ocean's chemistry, delivered up through the cracks and the chaos, and left sitting on top where a sensitive instrument, even one far away, might read it. The thickness of the ice controls how much of that delivery actually happens, but as long as any of it happens at all, the surface becomes a laboratory bench where the ocean lays out its ingredients. That is the bridge to everything that follows. We have a global ocean, warmed by tidal flexing, sealed under a shell of unknown but finite thickness, and we have strong signs that material passes between the sea and the surface, at least in the young, broken regions. The question stops being whether there is water and becomes what is in the water. Is that ocean just salty, or is it also stocked with the chemistry that living things are built from? Before we can weigh that, we should look honestly at the ocean itself, at how vast and strange this hidden sea really is. It is easy to say the word subsurface ocean and move on. It is harder and more worthwhile to picture what is actually down there, a body of dark water on a scale that dwarfs anything on our own planet. Try to picture the ocean itself. Beneath the ice of Europa lies a globe-spanning sea of liquid salt water, and its scale is hard to hold in the mind. Europa is a small world, smaller than our moon, yet its ocean may contain more than twice as much water as all of Earth's oceans put together. Every sea and every drop of every ocean on our planet poured together would not fill it. All of that water is packed into a shell, wrapped around a body you could fit comfortably inside the outline of the United States. The reason so much fits is depth. Earth's oceans are a thin film by comparison, on average only a couple of miles deep, spread over the surface of a large planet. Europa's ocean is thought to be something like 60 miles deep, perhaps more, a single continuous layer with no continents to interrupt it, and no shallows in the way we know them. If you could stand on the rocky floor at the bottom, the water above you would reach 10 times higher than the deepest trench in any sea on Earth. It is less like our oceans and more like a planet-sized drop of water with a crust of ice frozen around it, and it is dark. No sunlight reaches the floor of Europa's ocean. Even at the top of the water, just beneath the ice, almost nothing filters through miles of frozen shell. Deeper down, there is no light at all, only cold black water under crushing pressure in perpetual, total night. On Earth, nearly every ecosystem is powered in the end by sunlight, by plants, and other life that turn light into food. In Europa's ocean, sunlight is simply not an option. If anything lives there, it lives without ever knowing the sun. The water is salty, and the salt is a clue to more than just conductivity. Those dissolved salts had to come from somewhere, and the most likely source is the rock at the bottom. Water in contact with rock slowly leaches minerals out of it, the way water pulls flavour from tea leaves, and over billions of years that steady chemistry can load an ocean with dissolved material. The presence of salt is a sign that the ocean is not sealed off from the rock beneath it. The two are in contact, and they are reacting. That contact will matter greatly when we ask what else the water might have picked up. It is worth pausing on how long this sea has likely existed. The tidal heating that keeps it liquid has been running since Europa formed, more than 4 billion years ago, and there is no reason to think it ever stopped for long. So this is not a young ocean or a temporary one. It is one of the oldest, most stable bodies of liquid water anywhere we know of, older than the first cells on Earth, sitting undisturbed in the dark for a span of time the human mind struggles to take in. Whatever chemistry got started in that water has had almost the entire history of the solar system to unfold. That combination is what makes Europa so compelling. Not just water, but a vast, ancient, stable ocean in constant contact with rock, warmed from within, and possibly exchanging material with the surface above. It is beginning to sound less like a frozen curiosity and more like a place where things could happen. But a warm, salty, rocky-bottomed ocean is still only a stage. Whether anything could actually live on that stage depends on what the seafloor is like, and on whether the bottom of Europa's ocean offers not just minerals but energy. On Earth, some of the most surprising life we've ever found clusters in the dark at the bottom of the sea, around cracks in the rock where heat and chemistry pour out. The floor of Europa's ocean may hold the same kind of place. At the bottom of Europa's ocean is rock. This is a crucial point, and it sets Europa apart from some other icy worlds. The water does not rest on more ice. It rests on a rocky mantle, a body of stone and metal much like the interior of a small planet, and the ocean sits directly against it. That boundary, where dark water meets warm rock, is one of the most interesting places in the solar system, because on Earth, boundaries exactly like it teem with life. Consider what happens on our own seafloor. In the deep, sunless parts of Earth's oceans, there are places where the crust cracks and heat from within the planet rises up. Seawater seeps down into the hot rock, gets superheated, dissolves minerals and gases, and comes roaring back out through openings we call hydrothermal vents. Around these vents, in total darkness, thousands of feet down, whole thriving communities of life have been found. Tube worms, crabs, shrimp, and vast mats of microbes crowd around the mineral-rich water. None of them use sunlight. They live in the end off the chemistry that comes out of the vents, off energy locked in the minerals and gases from the rock. This was one of the great discoveries of ocean science, because it proved that life does not strictly need sunlight. It needs an energy source and the right chemistry, and a hydrothermal vent supplies both. Some scientists even suspect that life on Earth may have gotten its start at vents like these, in the dark, long before anything learned to use the sun. If that is true, then the recipe for beginning life might be a rocky ocean floor with heat and cracks running through it, and Europa may have exactly that. The same tidal flexing that warms Europa's ocean should also heat its rocky interior. Just as Io's rock is squeezed hard enough to erupt in volcanoes, Europa's mantle is flexed too, more gently, but perhaps enough to keep the seafloor warm and active. If so, then heat is leaking out of the rock into the bottom of the ocean right now, possibly through vents very much like the ones on Earth. Water would circulate through the hot rock, pull minerals and chemical energy out of it, and carry them into the sea. The ocean floor of Europa could be dotted with warm, chemically rich oases in the endless cold and dark. That is why the rocky floor matters so much for the question of life. An ocean alone is a place to live. An ocean in contact with warm reactive rock is a place to make a living. It offers not just water, but energy and raw materials, delivered from below, entirely independent of the faraway sun. Everything we know about the vent communities on Earth says that if you provide those conditions, life can at least survive, and might even begin. We have not seen these vents on Europa. No spacecraft has looked at its ocean floor, and none can, at least not yet. This remains a reasonable expectation built on solid physics and a strong earthly example, not a confirmed observation, and it is fair to hold it as a hope rather than a fact. But the pieces fit together with unusual neatness. A warm, salty, ancient ocean, resting on flexed and heated rock in the dark for billions of years. Which brings us to the heart of the matter. We have talked about water and we have talked about energy from the rock below. But life as we understand it needs one more thing, a particular set of chemical building blocks. For decades, scientists could argue that Europa had the water and probably the energy, yet they had no proof it had the chemistry. That missing piece is what the James Webb Space Telescope was about to change. To see why its discovery landed so hard, we first have to be clear about what life actually requires, and why one ingredient in particular had gone unaccounted for. When scientists ask whether a place could support life, they're really checking a short list of requirements, drawn from the only example we have, which is life on Earth. Strip away the details and it comes down to three things. Life needs liquid water, life needs a source of energy, and life needs a particular set of chemical building blocks, above all the element carbon. Where all three come together and stay together long enough, living things become at least possible. Europa was a strange case, because for a long time it seemed to have two of the three, with the most important building block unaccounted for, the water we have covered. Europa's global ocean is as good a supply of liquid water as anywhere beyond Earth, vast and ancient and stable. The first box is firmly checked. The energy too looks promising. Tidal heating warms the ocean, and the flexed rocky seafloor may host hydrothermal vents that pour out chemical energy in the dark, the same kind of energy that feeds life at the bottom of our own seas. That is the second box, checked with reasonable confidence. 2 of the 3 requirements seemed to be in place. The third was the problem. Life on Earth is built on carbon. Every living thing you've ever seen is essentially an elaborate structure of carbon atoms linked into the molecules that make up cells, from the proteins in your muscles to the code in your genes. Carbon is the scaffolding of biology. Without a supply of it, in a usable form, the chemistry of life as we know it simply cannot get started. So the pressing question for Europa became whether its ocean actually contained carbon, and if so, where that carbon came from. This mattered more than it might sound, because not all carbon is equally useful, and not all sources mean the same thing. Comets and asteroids carry carbon, and they crash into every world in the solar system, Europa included. So even if you detected carbon on Europa's surface, you would face a nagging doubt. Did that carbon come from the ocean, welling up from inside, part of the moon's own chemistry? Or was it just debris sprinkled on from space, sitting on the ice like dust on a windowsill, telling you nothing about the sea below? Carbon delivered from outside would be almost meaningless for the question of habitability. Carbon rising from within would be everything. For habitability, you want the carbon to be part of the ocean's own inventory, dissolved in the water, available to any chemistry that might be underway down there. External carbon lands on top and mostly stays there, locked in surface ice, cut off from the sea. Internal carbon means the ocean is not just water and salt, but water and salt, and the raw material of life, stocked and waiting. The whole weight of the question rested on telling those 2 possibilities apart, and that is a hard thing to do from far away. You cannot dip a cup into Europa's ocean. You cannot land and drill. What you can do, if you have a sensitive enough instrument, is study the light coming off the surface and read the chemistry written into it. If carbon were present on the surface, the right telescope could detect it. And if that carbon were concentrated in the young, broken regions where the ocean is thought to reach the top, rather than scattered evenly like fallout from space, then its location would betray its origin. The pattern would tell you the source. That was the opening. It required an instrument powerful enough to take the faint light from a small distant moon and split it finely enough to pick out the fingerprint of carbon and to map where on the surface that fingerprint was strongest. No telescope on Earth or in space could do it well enough, until one particular observatory reached its post 1,000,000 miles from Earth and turned its golden mirror toward Jupiter. To understand what it found, we need to understand the machine itself and the quiet, powerful trick it uses to read the chemistry of worlds it will never touch. The instrument that changed the Europa story is the James Webb Space Telescope, the largest and most powerful telescope ever sent into space. It launched at the end of 2021 and travelled to a special point about 1,000,000 miles from Earth, 4 times farther away than the Moon, where it can sit in stable darkness and stare at the universe without our planet getting in the way. Its main mirror is over 21 feet across, built from 18 gold-coated hexagonal segments that unfolded in space like a flower, and it is shielded from the sun's heat by a sunshade the size of a tennis court. What sets Webb apart for our purposes is that it sees in infrared. Infrared is light with wavelengths a little longer than the reddest colour your eyes can detect, the kind of light you feel as warmth from a fire even with your eyes closed. Human eyes cannot see it, but it carries a great deal of information, and crucially, different molecules leave their marks in the infrared part of the spectrum. Webb was built to gather this light with extraordinary sensitivity, which is why it can study the faint warmth of the most distant galaxies. That same sensitivity can be turned on something much closer, like a moon of Jupiter. The trick Webb uses to read chemistry is called spectroscopy, and once you understand it, a great deal of astronomy makes sense. When light shines on a material or reflects off it, the molecules in that material absorb certain specific wavelengths and leave others alone. Each kind of molecule absorbs its own particular set, like a barcode. Carbon dioxide absorbs at one set of wavelengths. Water ice absorbs at another. Ordinary salt affects the light in its own way, so if you can spread out the light from an object into all its separate wavelengths and see which ones are missing, you can read off which molecules are present. You're identifying substances by the shadows they cast in the light. Webb carries an instrument built exactly for this, called the Near-Infrared Spectrograph, usually shortened to NIRSpec. It takes incoming infrared light and fans it out into a detailed spectrum, revealing the pattern of absorption in fine detail. A companion instrument, the Near-Infrared Camera, or NIRCam, takes the sharp images that show where on the Moon each measurement comes from. Together they let scientists not only detect a molecule but locate it, building a map of where a given chemical sits across the face of a world. This is a genuinely remarkable thing to be able to do. Without leaving its post a million miles from Earth, Webb can take the faint sunlight reflecting off the icy surface of Europa, more than 500 million miles away, spread that light into its spectrum, and pick out the chemical fingerprints hidden in it. It can tell water ice from carbon dioxide from salt, and it can tell you which patches of the Moon hold more of each. It is chemistry performed at a distance no human will travel in a lifetime, using nothing but captured light. There is a limit worth naming. Spectroscopy like this reads only the surface, the top thin layer of ice that the light actually touches. It cannot see down into the ocean directly, so whatever Webb detects is surface chemistry, and its value depends entirely on that earlier idea that the surface carries samples of the interior delivered up through the cracks and the chaos terrain. If the surface and ocean are connected, Webb's reading of the top becomes a window into the deep. If they are not, it reads only the skin. With this understanding in hand, we can finally get to what happened in 2023, when two separate teams of scientists turned Webb toward Europa, spread its reflected light into a spectrum, and went looking for the one ingredient that had been missing from the recipe for life. In 2023, the results came from not one but two independent teams, working with the same powerful telescope and arriving at conclusions that reinforced each other. That doubling matters in science. When two groups, analysing the data in their own ways, reach the same answer, the answer stands on much firmer ground than any single study could provide. Both teams published their findings on the same day, the 21st of September, in the journal Science, and together they reshaped how seriously we take Europa as a home for life. One team was led by Samantha Trumbo, a planetary scientist then at Cornell University, working with Michael Brown of the California Institute of Technology. Brown is well known in astronomy, in part for his role in the events that reclassified Pluto, and he has spent years studying the surfaces of icy bodies. Trumbo had already been piecing together the chemistry of Europa's surface using earlier observations, including the Hubble detection of ocean salt. For them, Webb was the tool that could finally sharpen a blurry picture into something clear. The other team was led by Geronimo Villanueva of NASA's Goddard Space Flight Center. Villanueva's group came at Europa with a broad set of goals. They wanted to survey its surface chemistry, and they also wanted to hunt for something more dramatic, plumes of water erupting from the Moon into space, which we will come to shortly. Two teams, two sets of eyes, one small distant moon, and the sensitive infrared gaze of the Webb telescope trained on all of it. Their basic method was the one we just described. They pointed Webb at Europa, gathered the infrared sunlight reflecting off its icy surface, and used the near-infrared spectrograph to spread that light into a detailed spectrum. Then they searched the spectrum for the barcodes of specific molecules, and they used the accompanying images to see where on the Moon each signal was strongest. The work is painstaking. A moon like Europa is small in Webb's view, and the signals are faint, so teasing a clear chemical map out of the data takes careful analysis and cross-checking. What both teams found, written plainly in the light, was carbon dioxide. The frozen surface of Europa carries carbon dioxide ice, the same compound you know as the bubbles in soda and the gas you breathe out, locked solid on the Moon at its deep freeze temperatures. The signal was clear enough that both groups agreed on it. After all the years of arguing whether Europa's chemistry included the essential element of carbon, here it was, detected directly, sitting on the surface for a telescope to read. The teams even saw carbon dioxide in more than one form. Some of it appeared as pure crystalline ice, and some of it was mixed and altered, bound up with other materials in a more complex state. That detail carries information about how the carbon dioxide got there, and how it has been treated by the harsh surface environment since. It is the difference between a fresh coat of frost and a weathered stain, and reading which helps trace the compound's history. Finding carbon on Europa was the answer to a question decades old. But by itself, a detection of carbon dioxide was not yet the thing that made scientists sit up. Carbon dioxide could, in principle, have come from outside, delivered by the same comets and micrometeorites that pepper every world. The detection filled in the missing ingredient, but it did not yet say whether that ingredient belonged to Europa's ocean or was merely dusted on from space. To answer that, the teams did not just detect the carbon dioxide, they mapped it, and the map is where the story turns. The moment the finding became powerful was when the teams looked at where the carbon dioxide was, not just that it was there. If carbon dioxide had rained down onto Europa from space, from comets and small impacts over the ages, you would expect to find it spread fairly evenly across the whole surface, like dust settling uniformly over everything in an unused room. That is not what the map showed. The carbon dioxide was not spread out. It was concentrated, piled up heavily in specific regions and thin or absent elsewhere. Something local was putting it there. Above all, it was concentrated in one place we have already met. The strongest signal of carbon dioxide came from Tara Regio, the yellowish, mottled patch of chaos terrain where the surface has plainly been broken up and refrozen, and where the Hubble Space Telescope had earlier found signs of ocean salt. A second, smaller concentration showed up in a neighbouring disrupted region called Panis Regio. The carbon dioxide was tied tightly to exactly the kind of young, shattered terrain where the ocean is thought to reach closest to the surface. Think about what that pattern means. External carbon, falling from space, has no reason to prefer the chaos terrain. It would land everywhere, indifferent to the geology below. But carbon coming up from inside the moon would appear precisely where the interior connects to the surface, in the broken zones where material is carried up and set down. The location of the carbon dioxide matches the second story and contradicts the first. The map itself argues that the carbon came from below, from Europa's own interior, most likely from the ocean. There was more in the details. The carbon dioxide sits in geologically young terrain, freshly resurfaced, which suggests it arrived recently rather than accumulating slowly over billions of years. Carbon dioxide is not stable forever on Europa's surface. The radiation and conditions there tend to destroy or drive it off over time, so the fact that we see it at all implies it was delivered recently and may still be arriving. A fresh, ongoing supply from within fits far better than an ancient dusting from outside. Put the pieces together and the conclusion is striking. The carbon dioxide on Europa most likely originated in the subsurface ocean, was carried up through the disrupted crust of Tara Regio, and was deposited on the surface in geologically recent times. It was not delivered by meteorites. It is a sample, however processed, of the ocean's own carbon, brought up to where a telescope a million miles away could read it. The missing ingredient was not only found, it was traced back to the sea. This is the finding at the centre of the whole story, the thing the title points to. The ocean of Europa is not merely water and salt. It carries carbon, the element that life is built from, and that carbon is finding its way to the surface. Every requirement on the shortlist for life now has evidence behind it. Liquid water confirmed by Galileo's magnetic measurements. Energy from tidal heating and the likely vents on the seafloor. And now carbon, the building block, detected directly and tied to the ocean below. None of this means there is life on Europa. It is worth saying clearly. What it means is that Europa has, as far as we can tell, the ingredients and the conditions that life requires, all in one place, all at once, and that the ocean holding them is old enough to have done something with them. That is a very different statement from a world merely having water. It moves Europa from a place with potential to a place with a real case. To make that case airtight, though, scientists wanted to understand this Tara Regio connection far more deeply. Why there and not elsewhere? What else is concentrated in that same strange patch of broken ice? And what do the salts, already found in the very same place, have to say when you set them beside the carbon? The address keeps coming up for a reason, and the next part of the story is about reading everything written at that one location on the map. Years before Webb turned its mirror on Europa, another telescope had already marked Tara Regio as odd, and it did so because of a colour. Most of Europa's surface is fairly white or faintly blue, the look of clean water ice. Tara Regio is yellowish. That tint is small, but to a careful eye it is a signal, because pure water ice does not turn yellow on its own. Something else is mixed into the ice there, and the colour is a clue to what. The clue was chased down using the Hubble Space Telescope, in work that Samantha Trumbo was part of before she ever used Webb. The team compared how Tara Regio reflects light with what happens to different materials in the laboratory, and they found a strong match with common table salt, sodium chloride, the same white grains you keep in your kitchen. On Earth, table salt is white. But when you take sodium chloride and blast it with radiation, the kind of radiation that constantly rains down on Europa from Jupiter, it changes. Defects form in its crystal structure, and it turns yellow. The colour of Tara Regio is the colour of ordinary salt that has been irradiated for a long time. That finding was quietly important. Salt on the surface, in a broken chaos region, points straight back to the ocean. Sodium chloride does not appear on a frozen moon by chance. It has to be dissolved in water and then carried up, which means the yellowish stain of Tara Regio is very likely dried sea salt, left behind where ocean water reached the top and froze. Europa's hidden sea, in other words, seems to be a salty sea much like our own, not some exotic brew, but water with sodium chloride dissolved in it. Now set the two discoveries side by side, because this is where they become powerful together. Hubble found ocean salt concentrated in Tara Regio. Webb found ocean carbon concentrated in the very same place. Two different telescopes, two different chemicals, two different research efforts, and both point to the same patch of broken ice as the spot where the interior comes up to meet us. When independent clues line up on the same location like that, the case stops resting on any single measurement. It becomes a pattern, and patterns are what scientists trust. The agreement also tightens the argument about where the carbon came from. If the carbon dioxide were random fallout from space, there would be no reason for it to share an address with the salt. Space debris does not know or care where the salt is. But if both the salt and the carbon are being delivered from the ocean, through the same cracks and the same disrupted terrain, then finding them together is exactly what you would expect. The salt was the first witness, and the carbon is the second, and they tell the same story. So Tara Regio has become the most studied few hundred miles on all of Europa. It is a window, or as close to a window as we have, a place where the surface and the sea appear to be trading material, leaving salt and carbon on the ice for our instruments to read. Everything we most want to know about the ocean is written, faintly, in that yellowish patch. The question then becomes what all of this adds up to. We have salt from the ocean and carbon from the ocean, sitting together in the same broken ground. Taken alone, each is a chemical curiosity. Taken together, they begin to describe the character of the sea itself, and that description is what turned Europa from a place with water into a place with a real chemistry, the kind of chemistry that living things are built on. Bring the pieces together and a portrait of the ocean starts to form. Beneath the ice lies a body of salty water that also carries carbon, and both facts come from reading the surface where the sea reaches up. A sea that holds dissolved salt and dissolved carbon is not a sterile tank of pure water. It is a chemically active ocean, stocked with the same broad kinds of ingredients that fill the oceans of Earth, the ingredients from which the chemistry of life is assembled. Carbon is the ingredient that matters most here, because of what it can do. Carbon atoms link together and bond with other elements more readily than almost anything else, forming long, complex molecules that can store information and drive reactions. Every living thing we know is built from these carbon-based molecules. A world can have water and warmth and still be a dead end for life if it lacks a usable supply of carbon. Europa, we now have good reason to think, does not lack it. The carbon is there, dissolved in the water, and the ocean has had billions of years to work with it. There is a deeper point about the ocean's health as a chemical system. Life, at bottom, runs on chemical imbalances, on having a source of one kind of chemistry meeting a source of another, so that energy can flow across the gap. Europa may have exactly that. From below, the rocky heated seafloor could feed the water with chemicals hungry to react. From above, as we'll see, the harsh surface makes chemicals of the opposite kind, which may sink down into the sea. An ocean caught between those two supplies is an ocean with a battery, a standing imbalance that could power the reactions life depends on. None of this crosses the line into a claim of life, and it is worth being careful about that line. Having the ingredients is not the same as having the meal. Earth had water and carbon and energy for a long stretch before anything living appeared, and we still do not fully understand how the leap from chemistry to biology happened even here. So the correct statement about Europa is measured. It has the water, it has the energy source most likely, it has the carbon, it has the imbalance that could drive reactions. Whether any of that ever became life we do not know, and we cannot know from a spectrum alone. But the change in how scientists regard Europa is real, and it is the reason this discovery drew so much attention. For decades, Europa was a strong maybe, a world with an ocean whose chemistry was a blank. The carbon detection filled in the most important blank. It moved Europa firmly into the small group of places in the solar system where, as far as we can measure, the conditions for life are present all at once. That is a short list, and Europa now sits near the top of it. There was one more thing the scientists using Webb had hoped to catch, something that would have let them sample the ocean far more directly than reading frozen salt and carbon off the surface. If Europa were venting its ocean into space, even in small amounts, a telescope might see it and even taste what came out. So one of the teams went looking during the same observations for plumes of water rising off the moon. What they found, and did not find, is the next turn in the story. While Samantha Trumbo and Michael Brown focused on mapping the surface chemistry, the team led by Geronimo Villanueva had a second target in mind. They wanted to catch Europa in the act of spraying its ocean into space. The idea is that if water from the sea escapes through cracks in the ice, it would erupt upward as a plume, a fountain of vapour and tiny ice grains rising off the surface. A plume would be a gift to science, because you would no longer have to guess what the ocean contains by reading old salt on the ice. You could point a telescope at the plume and read the ocean's water almost directly. There was good reason to hope. The Hubble Space Telescope had reported possible signs of plumes on Europa on a few occasions, tentative hints in 2013, 2016 and 2017. These were faint and hard to confirm, glimpses at the edge of what Hubble could detect, but they raised the tantalizing possibility that Europa, like some other icy moons, might be leaking its sea into space where we could sample it. When Webb, far more sensitive than Hubble, turned toward Europa, catching a plume was near the top of the wish list. Webb did not see one. During the observations, the telescope found no sign of an erupting plume, no fountain of water, nothing venting off the surface at the level Webb could have detected. For a team hoping to taste the ocean, that was a quiet disappointment, the bittersweet edge of an otherwise rich result. They had found carbon, a major prize, but the more dramatic hope of catching the moon mid-eruption did not come through on that day. It is important to read the non-detection correctly, and the scientists were careful to do so. Not seeing a plume during a particular observation does not mean Europa never has plumes. It may mean the plumes come and go, erupting only now and then, so that a telescope looking on a given day simply catches the moon at rest. It may mean any plumes are smaller or rarer than we hoped, or the earlier hints may have been something else entirely. the honest conclusion is limited. On the occasion Webb looked, Europa was not visibly venting, and that is all the data can firmly say. This is a good example of how careful science actually works, and how different it is from a tidy story. The plume question is still open. Europa might well erupt, on a schedule we have not pinned down, and future observations might yet catch it. The failure to see one is a real result worth reporting, but it closes no doors. It simply tells us that the easy shortcut sampling a fountain of ocean water from afar was not available that day, and that if we want to reach the ocean, we may have to work harder and go closer. So the plume hunt came up empty, and the carbon finding stood as the headline. But the same Webb data held one more surprise, and this one was stranger than the carbon, because it seemed to break a rule that laboratories on Earth had spent decades establishing. Alongside the carbon dioxide in the same warm, broken terrain, Webb detected another compound sitting exactly where the textbook said it should not be. That misplaced chemical would send scientists back into the laboratory to figure out how it got there. The extra surprise in the Webb data was hydrogen peroxide. It is the same compound sold in brown bottles as a mild antiseptic, 2 hydrogen atoms and 2 oxygen atoms bound together, and it forms naturally on icy worlds when radiation breaks apart water molecules and the fragments recombine. Finding hydrogen peroxide on Europa was not itself shocking. Scientists had expected some. What shocked them was where Webb found it, because the peroxide was piled up in precisely the wrong place. For decades, laboratory studies had built a clear expectation. When you make hydrogen peroxide in ice by hitting it with radiation, the cold matters. Colder ice holds onto more peroxide, while warmer ice holds less, because warmth tends to break the fragile molecule apart. From that rule, the prediction for Europa was straightforward. The most hydrogen peroxide should sit at the frigid poles, where the ice is coldest, and the least should sit around the warm equator. It was a tidy, well-tested idea, the kind scientists felt safe leaning on. Webb found the opposite. The strongest hydrogen peroxide signals came not from the cold poles, but from the warm equatorial region, and above all from the chaos terrain around Tara Regio, the same broken, yellowish, carbon-rich, salt-stained patch that keeps returning in this story. The warmest, most disrupted ground held the most of a chemical that was supposed to prefer the cold. The rule that had stood for decades appeared to be broken, at least here. When a reliable expectation fails like that, it is not a nuisance, it is a lead. A broken rule means some ingredient in the real world is missing from the laboratory version, some factor that changes the outcome. The question became obvious. What was different about the warm chaos terrain of Europa that let it hoard hydrogen peroxide against every prediction? The answer, scientists suspected, might be sitting right next to the peroxide on the map. Because the very same regions that were rich in hydrogen peroxide were also the regions rich in carbon dioxide. The two compounds shared an address, just as the carbon and the salt had. That overlap was the crucial hint. It suggested that the carbon dioxide was not just a passive passenger on the surface, but might be an active player, somehow helping the hydrogen peroxide survive where it otherwise should not. Correlation on a map is not proof of a connection, and the scientists knew that. Two things can sit in the same place for unrelated reasons, but the pattern was strong enough and strange enough to demand a proper test, the kind you cannot run on a moon 500 million miles away. So the puzzle passed from the telescope to the laboratory. To find out whether carbon dioxide could really protect hydrogen peroxide in cold ice, someone needed to recreate a small piece of Europa on Earth, to freeze water and carbon dioxide together, blast it with radiation at Europa's temperatures, and watch what happened to the peroxide. That is a delicate, patient kind of work, done in a specialised cold laboratory by researchers willing to chase a single strange measurement to its source. And it is exactly the work that a graduate student in Texas set out to do, in a facility built for pretending to be the surfaces of distant worlds. The chase led to a laboratory in San Antonio at the Southwest Research Institute, in a facility whose long name is usually shortened to the Center for Laboratory Astrophysics and Space Science Experiments. It is a place built to imitate the surfaces of distant frozen worlds. Inside sealed chambers, researchers can deposit thin films of ice at the deep freeze temperatures found out at Jupiter, then bombard them with radiation and watch, molecule by molecule, what the ice does. It is a way of bringing Europa down to a benchtop small enough to run a real experiment on. The experiment was taken up by Bereket Mamo, a graduate student at the University of Texas at San Antonio, working with the institute along with his advisor, Ujjwal Raut, and their colleagues. Mamo had noticed the same thing the Webb map showed, that the chaos terrains rich in hydrogen peroxide were also rich in carbon dioxide, and he set out to test whether the two were linked. He won a NASA grant to fund the work, and then he did the patient thing. He made ices with different amounts of carbon dioxide mixed in, cooled them to Europa's temperatures, irradiated them, and measured how much hydrogen peroxide each one produced and kept. The result was clear, and it confirmed the suspicion. Even a small amount of carbon dioxide mixed into the water ice sharply boosted how much hydrogen peroxide the ice held onto. At temperatures like those on Europa's surface, the carbon dioxide was not a bystander, it was actively helping the peroxide survive. That single laboratory finding explained the strange map. Hydrogen peroxide gathered in the warm chaos terrain not in spite of the warmth, but because that terrain was also loaded with carbon dioxide, and the carbon dioxide tipped the balance. The reason it works comes down to stray electrons. When radiation slams into ice, it knocks electrons loose, and those loose electrons tend to find and break apart hydrogen peroxide molecules, destroying them soon after they form. Carbon dioxide, it turns out, behaves like a scavenger. Its molecules grab the wandering electrons and hold them, taking them out of circulation before they can wreck the peroxide. With the carbon dioxide mopping up the destructive electrons, the hydrogen peroxide is shielded and it accumulates. The presence of one ocean-derived chemical is protecting another chemical made by radiation. This is a small, specific result, published in a planetary science journal in the summer of 2025, and it is worth admiring for its ordinariness as much as its cleverness. No spacecraft, no billion-dollar mission, just a graduate student, a cold chamber, and a careful question, solving a puzzle that a telescope a million miles away had handed down. The whole chain is a nice picture of how the field really moves. Webb sees something strange. The strangeness is a clue. Someone builds a tiny Europa on a table and tests the clue until it makes sense. But the finding is more than a tidy explanation of a map. It hints at something happening on Europa that could matter enormously for the ocean below. The surface is not just collecting chemicals, it appears to be a chemical factory, taking ocean carbon and radiation and building oxidants like hydrogen peroxide, the kind of energetic molecules that life can use for fuel. And if there is any way for those surface-made oxidants to travel back down into the sea, then the connection between the top of Europa and its hidden ocean becomes a two-way street, with consequences that reach all the way to the question of whether anything could live down there. Picture the whole thing as a loop. Carbon rises from the ocean through the cracks and reaches the surface, where it freezes into the ice of the chaos terrain. There, Jupiter's radiation goes to work, splitting water and building energetic molecules, and the carbon helps those molecules, the oxidants like hydrogen peroxide and oxygen, survive and gather. Then, wherever the ice cycles back down, through the same cracking and refreezing that broke the terrain in the first place, some of those oxidants may be carried back into the ocean. Material goes up, gets transformed by radiation, and comes back down changed. It is a cycle, powered from above by Jupiter and from below by the moon's own heat. Why does that loop matter so much? Because of what oxidants do. An oxidant is a molecule that is hungry to react, one that can strip energy out of other chemicals when the two meet. Life, at its core, is a controlled way of running exactly those reactions and capturing the energy released. On Earth, the oxygen you breathe is an oxidant, and your body lives by reacting it with food. An ocean that receives a steady supply of oxidants from above has, in effect, one half of a battery delivered to it, free of charge, courtesy of the radiation overhead. The other half of the battery could come from the sea floor. If the rocky bottom of Europa's ocean hosts hydrothermal activity, as the tidal heating suggests it might, then chemicals of the opposite kind, the ones eager to give up electrons rather than take them, would be seeping up from the rock. Bring the two halves together in the water, oxidants sinking from above and their counterparts rising from below, and you have a standing chemical imbalance running through the whole ocean. That imbalance is a source of energy, and a source of energy is one of the things life requires. Ujjwal Raut, the advisor on the laboratory work, described the finding as evidence of just this kind of chemical cycle, in which material rising from the ocean is irradiated at the surface, turned into oxidants, and then potentially cycled back down where it could react with chemicals coming off the seafloor. It is a way for Europa to keep feeding its own ocean chemical energy over long stretches of time, without any sunlight at all. The Moon would be running a slow, planet-wide chemistry set, driven by gravity and radiation instead of the Sun. This must be held carefully, because several links in the chain are still uncertain. We do not know for sure that hydrothermal vents exist on Europa's seafloor. We do not know how efficiently, or even whether, surface oxidants actually reach the ocean, since that depends on how the thick or thin ice cycles and connects. Each step is plausible and grounded in real chemistry and real measurements, but the full loop is a well-supported idea rather than a confirmed fact. That distinction is worth keeping clear so the wonder stays honest. Still, the shape of it is striking. What began as a single odd detection, hydrogen peroxide in the wrong place, has opened into a picture of Europa as a chemically alive world, cycling ocean carbon up to the surface and energy back down. And just as scientists were settling into that picture, a fresh look at the Webb data, using a sharper method, suggested that the carbon story might be even bigger than Tara Regio alone. The ocean's fingerprints, it seemed, might be spread more widely across the Moon than the first maps had shown. Early in 2026, a new group of researchers went back to Webb's observations of Europa with a sharper set of tools. The team, led by Gideon Yoff, applied a technique called spectral decomposition to the data. The idea is to take the light coming off Europa and carefully separate out the overlapping fingerprints of many different materials at once, untangling which part of the signal belongs to water ice, which to carbon dioxide, and which to other compounds. By working across 9 separate bands of the spectrum, they could reconstruct in more detail than before where each chemical sits on the Moon's leading face. What they found extended the carbon story beyond its first home. The earlier work had pinned carbon dioxide most strongly to Tara Regio and its neighbour. The newer analysis suggested that carbon dioxide is present more widely across the surface than that first map implied, showing up in other regions too, though still tied to areas where the surface appears disturbed. Rather than a single isolated patch of ocean carbon, Europa began to look like a moon with carbon distributed across a number of sites where the interior has reached up. If that holds, it strengthens the central conclusion. A single concentration of carbon in one strange region could, with effort, be explained away as a local oddity. Carbon appearing in multiple disrupted regions, each one a place where the crust has been broken and resurfaced, fits the picture of an ocean that is exchanging material with the surface in many places, not just one. The trading of chemistry between sea and surface would then be a general feature of Europa, part of how the whole Moon works, rather than a quirk of Tara Regio alone. It is right to be cautious here, because this work is recent and was shared as a preprint, a version of a study posted for other scientists to examine before it has finished the full process of peer review. That process matters. Other researchers will check the methods, test whether the wider carbon signals are real or partly artifacts of the analysis, and either confirm or revise the conclusions, so the wider map should be treated as a promising new result rather than a settled one. It points in the same direction as everything before it, which is encouraging, but it has not yet been through every check. What the new study shows, more than any single detail, is that the Webb data on Europa are still giving up their secrets. The same observations, revisited with better techniques, keep yielding more. This is common in astronomy. A rich data set is not read once and set aside. It is returned to again and again as methods improve, and each pass can pull out signals that the first look missed. Europa's spectrum, gathered in a few precious hours of telescope time, will likely be studied for years yet. All of this careful, incremental work, the mapping and remapping, the laboratory tests, the cautious language of preprints and peer review, sits oddly against the word that surrounds this whole subject in the wider world. The story reaching most people was not one of patient science. It was a story of scientists supposedly panicking over what Webb had found. It is worth stopping near the end to ask plainly whether anyone was panicking at all, and if not, what the real reaction was, and why the quieter truth is more interesting than the alarm. So, was anyone panicking? The plain answer is no. Nothing about the Webb discoveries at Europa caused fear or alarm among the scientists who made them. There was no emergency, no dangerous finding, no threat. The word panic belongs to headlines and thumbnails, where strong feelings sell a click, and it does not describe what happened in the offices and observatories where this work was done. What the scientists felt was closer to excitement, curiosity, and the particular satisfaction of a long-standing question finally getting an answer. If you read what the researchers themselves said, the tone is measured, even a little understated. Geronimo Villanueva spoke about how the degree to which Europa's ocean connects to its surface had long been a driving question in the field, and about how these findings spoke to it. Samantha Trumbo laid out carefully how the carbon lining up with the salt implied an internal source. There is real feeling in that work, the pleasure of a puzzle coming together, but it is the quiet kind. The most dramatic word anyone used was bittersweet, and that was about not catching a plume. The truth is that discoveries like this one usually arrive quietly, and that quietness is worth understanding. Science does not advance in sudden shocks so much as in careful steps, each one checked against the last. A team makes a measurement, another team confirms it. Someone runs a laboratory test, someone else reanalyzes the data. The excitement is real, but it is spread thin over months and years of patient work, and it rarely looks like panic from the inside. The people doing it are too busy testing whether they are right. What genuinely shifted, and it did shift, was Europa's standing. Before Webb, Europa was a world with an ocean and an unknown chemistry. After Webb, it is a world with an ocean known to carry carbon, the element life is built from, most likely sourced from the sea itself. That is a real change, and it moved Europa up the short list of places worth taking seriously in the search for life. But moving up a list is not the same as ringing an alarm bell. It is a reason to look closer, not a reason to be afraid. There is a lesson tucked inside the gap between the headline and the reality. The universe is strange and wonderful enough on its own terms that it does not need to be dressed up in false drama. The real Europa story, an ancient hidden sea, salty and carbon-rich, cycling chemistry with a shattered surface under the glare of Jupiter, is more interesting than any invented panic precisely because it is true. The wonder that lasts is the honest kind, the kind you can keep looking at without it falling apart. And there is more honest wonder still to come, because the discoveries we have talked about were all made from far away, by reading faint light. That distance is both the triumph and the limit of the story. To make the leap from a chemically promising ocean to any real understanding of what is down there, we will have to leave the telescope behind and go to Europa itself. Before we get to the spacecraft already on its way though, we should look squarely at the world it is heading into. Because Europa's surface is not just cold and strange, it is one of the most hostile places a machine, or anything else, could try to visit. Stand on the surface of Europa, and the danger you could not see would be the one that killed you fastest. It is not the cold, though the cold is severe, and it is not the thin air. It is the radiation. Europa orbits deep inside the most intense radiation environment of any planet in the solar system, and an unshielded human standing on that ice would absorb a lethal dose in a matter of days, perhaps less. The pretty pale marble sits inside an invisible storm. The storm comes from Jupiter. The giant planet has an enormous magnetic field, thousands of times stronger than Earth's, and that field traps charged particles, electrons and ions, and accelerates them to tremendous speeds. They form vast belts of radiation wrapped around Jupiter, and Europa orbits right through them. Every second, the moon's surface is scoured by these high-energy particles slamming into the ice. The reddish stain along the cracks, the yellowed salt of Tara Regio, all of it has been coloured and chemically altered by this relentless bombardment. That same radiation is why Europa's surface, on its own, is a poor place to look for living things. Any delicate molecule sitting exposed on top would be broken apart by the particle rain before long. If there is life on Europa, it is almost certainly not on the surface but down in the ocean, shielded by miles of ice from the storm above. The ice is not just a lid on the sea, it is a shield, and a thick enough shield is the difference between a protected ocean and a sterilized one. But the radiation is not purely destructive, and this is the twist that ties back to everything we have seen. The very same particle bombardment that would harm life on the surface is what drives the chemistry that could feed life below. When radiation breaks apart the water ice, it creates oxygen and oxidants like the hydrogen peroxide we followed earlier. The harsh surface is in effect a factory, using Jupiter's radiation as its power source to manufacture the energetic molecules that an ocean ecosystem might run on. The threat above and the possible fuel below are made by the same process. This is one of the more elegant ideas in the whole subject. A world can be hostile and generous at the same time, in the same act. Jupiter's radiation makes the surface deadly and simultaneously stocks it with oxidants. If those oxidants find their way down through the ice, the storm that would kill a surface visitor becomes a source of chemical energy for whatever might live in the dark sea. Europa's greatest hazard and its possible lifeline are two faces of the same thing. The radiation also shapes how we can explore. Any spacecraft sent to study Europa closely has to survive that same storm, and its sensitive electronics would be fried in short order without heavy protection. This single fact has driven the entire design of the mission now on its way, dictating how it is built, how it is shielded, and even the strange looping path it takes around Jupiter, rather than orbiting Europa directly. Before we follow that spacecraft, it helps to see how other worlds have handled the question of a hidden ocean, because Europa is not the only moon with a sea, and one small moon of Saturn showed us, in the most direct way imaginable, what such an ocean can hold. Far out at Saturn, there is a small, brilliant white moon named Enceladus, and it did something Europa has so far refused to do. It let us taste its ocean. Enceladus is tiny, only about 300 miles across, small enough to fit within a single country on Earth, and for a long time it seemed too little to be interesting. Then the Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered something remarkable near its south pole. Enceladus was spraying its ocean into space. From long cracks in the south polar ice, nicknamed the Tiger Stripes, great jets of water vapour and ice grains erupt continuously into space, fed by a subsurface ocean much like Europa's, and Cassini did the extraordinary thing. It flew directly through those plumes, again and again, sampling the material with its instruments as it passed. For the first time, a spacecraft tasted the ocean of another world without ever landing, catching the spray of a hidden sea in flight and reading what it was made of. What Cassini found in the plumes made Enceladus a sensation. The spray contained water, of course, but also salts, showing the ocean is salty and in contact with rock, and a variety of organic molecules, the carbon-based building blocks of life. It even found molecular hydrogen, which on Earth is produced when hot water reacts with rock at hydrothermal vents. That hydrogen was a strong hint that Enceladus has active vents on its seafloor right now, pouring out the same kind of chemical energy that feeds life at the bottom of our own oceans. In a small moon of Saturn, we found an ocean with water, salt, organics, and a likely energy source, all confirmed by direct sampling. Enceladus matters for Europa in two ways. First, it proves that the whole scenario is real, that a small icy moon can hold a salty, chemically rich ocean with hydrothermal activity, because we have measured one directly. The case for Europa's ocean, built mostly from clever indirect evidence, gains confidence from a sister world where the same story was confirmed by tasting it. Second, Enceladus shows the enormous value of a plume. Cassini learned more about that ocean by flying through its spray than any telescope could ever read off a frozen surface. That is exactly why the failure to find a plume at Europa stings, and why the tentative hints of one keep drawing attention. Europa's ocean is far larger than the ocean of Enceladus, holding perhaps 100 times more water, and it may be just as rich. But Europa has not offered us an obvious, reliable fountain to fly through. Its secrets stay mostly sealed under the ice, readable only in the faint chemistry that reaches the top. Where Enceladus handed Cassini a sample, Europa makes us work for every clue. So we are left in a particular position. We have strong evidence that Europa has the ingredients for life, gathered from telescopes and confirmed in laboratories, and we have a nearby example in Enceladus showing that such oceans are real and can be chemically alive. What we do not have for Europa is the close look. Everything we know still comes from far away, and there are hard limits on what distance can tell us. To understand why the next step has to be a spacecraft, it helps to be clear-eyed about what even the finest telescopes simply cannot do. Everything we have learned about Europa's chemistry, all of it, comes from reading light that bounced off the top of the moon. That fact carries a hard limit. Light reflecting from the surface only touches the outermost skin of the ice, a thin layer at the very top. Whatever a telescope reads, it reads from that skin and no deeper. Webb cannot see into the ocean. It cannot peer through miles of ice to the water below. It can only study the surface and infer from what the surface carries what might lie beneath. That inference rests on a chain of reasonable assumptions, and every link is a place where certainty leaks away. We assume the carbon and salt on the surface came from the ocean, because of where they sit and how they are distributed. It is a strong case, but it is a case built on patterns and probabilities, not on a sample of ocean water in hand. A skeptic could keep asking for more, and the honest answer from a telescope alone would run out. There is only so far you can go by reading the outside of a sealed box. Distance sharpens the limit. Europa is a small moon, and it lies hundreds of millions of miles from Earth. So even to the most powerful telescope ever built, it is a tiny target, its light faint and hard-won. Webb can detect that carbon is present and roughly where it concentrates, but it cannot map the surface in fine detail, cannot resolve small features, cannot watch a single crack over time. It is like trying to learn the layout of a house by studying a single dim photograph taken from across a city. You can tell a great deal, but not everything, and never the inside. There are questions that no telescope, however good, will ever settle from afar. How thick is the ice, really, and does it vary from place to place? Are there hydrothermal vents on the seafloor? Do surface oxidants actually reach the ocean? Is there a plume, erupting on some schedule we have not caught? And the largest question of all, is anything alive down there? A question that reading reflected light can never answer, no matter how long we look. These require getting close, measuring directly, and in some cases sampling the moon itself. This is not a criticism of telescopes. Webb did something extraordinary, extracting the chemistry of a distant ocean from a whisper of light, and it reshaped how seriously we take Europa. But a telescope is the beginning of an investigation, not the end. It tells you where to look and what to look for. It raises the questions sharply enough that answering them becomes worth an enormous effort. Having done that for Europa, it hands the work to a different kind of explorer, one that does not sit a million miles away but travels the whole distance and flies close enough to touch the storm, and that explorer is already on its way. While the scientists were still analysing Webb's data, a spacecraft built for exactly these questions was being finished, tested, and launched. It is the largest planetary spacecraft NASA has ever flown, and it is aimed straight at this moon, designed from the ground up to survive Jupiter's radiation and to answer the questions a telescope cannot. It left Earth not long ago, and it is crossing the solar system now, on a long curving road toward the pale marble we've been circling this whole time. On the 14th of October 2024, a Falcon Heavy rocket rose from the Kennedy Space Center in Florida, carrying the largest spacecraft NASA has ever built for a planetary mission. Its name is Europa Clipper, and its single purpose is to study this one moon. With its solar arrays unfolded, the spacecraft stretches about 100 feet from tip to tip, roughly the length of a basketball court, wingspans of solar panels sized to gather enough faint sunlight this far from the sun to run the whole machine. Europa Clipper is built around a problem we have already met, the radiation. To survive Jupiter's belts, its most sensitive electronics are locked inside a thick vault, with walls of aluminum and titanium, a small armoured room at the heart of the spacecraft shielding the delicate parts from the particle storm. Even so, the mission is designed to limit exposure, which is why Clipper will not orbit Europa directly. Circling the moon would keep it soaking in radiation constantly. Instead, it will orbit Jupiter on a wide, looping path and dart in for close passes, ducking into the storm to gather data and then swinging back out to safety. The road to Jupiter is long and indirect, because the spacecraft needs help from gravity to get there. Rather than flying straight, Clipper is taking a curving route through the inner solar system, borrowing energy from planets along the way. It swung past Mars in the spring of 2025, using the planet's gravity to bend and adjust its path. It is due to pass close by Earth at the end of 2026, picking up a further boost. Only after those two gravitational assists will it have the speed to coast out to Jupiter, where it is scheduled to arrive and slip into orbit in the spring of 2030. Aboard the spacecraft is a suite of 9 science instruments, along with an experiment that uses the radio system to probe the moon, and they are designed to work together on every pass. There are cameras to map the surface in detail far beyond anything a telescope can manage. There are spectrometers to read surface chemistry from close range, resolving what Webb could only glimpse. There is a magnetometer to measure Europa's magnetic response and confirm the ocean's depth and saltiness. And there is an instrument built to do something no mission has done at Europa, to look inside the ice. The mission has been a long time coming, decades in the planning, growing out of everything the Galileo spacecraft first hinted at, and everything the telescopes have since suggested. It represents an enormous investment of effort and money and hope, a deliberate decision that Europa is worth this much trouble. That decision was made because of the chain of clues we have followed, the smooth young surface, the salty ocean, the carbon from Webb. Each finding made the case stronger, until sending a flagship spacecraft to this one moon became not a wild idea but an obvious priority. Europa Clipper is crossing the solar system as you listen. It will not reach Jupiter for years yet, and it will not begin its real work at Europa until the early 2030s. But it is out there, a machine the size of a basketball court, carrying our questions across hundreds of millions of miles of empty space toward a frozen sea. When it arrives, it will do the things a telescope never could, and chief among them is finally measuring the one number that has haunted this whole story, the thickness of the ice, and searching for the ocean directly beneath it. The instrument that may matter most on Europa Clipper does not take pictures or read light. It is a radar, and its job is to see through solid ice. The instrument is called Reason, and it works by sending radio waves down into the ice shell and listening for the echoes. Radio waves pass through ice fairly well, but they bounce back sharply when they hit something different, like a boundary between ice and water, or a pocket of liquid trapped within the shell. By timing the echoes, Reason can build a profile of what lies below the surface, layer by layer, down toward the ocean. If it works as designed, reason could finally answer the question we left open long ago. How thick is Europa's ice? A clear echo from the boundary between ice and ocean would tell us directly how far down the sea begins and whether the shell is a few miles thick or many. It could also reveal whether there are lakes of liquid water trapped within the ice itself, the shallow pockets that some scientists think create the chaos terrain. After decades of arguing over a number no one could pin down, a spacecraft may simply measure it. Reason is only one of the tools, and the others fill in the rest of the picture. Over the course of the mission, Europa Clipper is planned to make close to 50 flybys of the Moon, each one shaped to pass over a different region, so that together they build up coverage of most of the surface. On some passes, the spacecraft will sweep as low as 16 miles above the ice, close enough to map features the size of a house and to read the surface chemistry in fine detail. Across the mission, the instruments aim to map more than 80% of Europa at resolutions no telescope could ever reach. The spacecraft will also watch for the thing Webb missed. If Europa vents plumes, even occasionally Clipper may catch one, and it carries instruments that could sample the material directly, tasting the ocean the way Cassini tasted Enceladus. It will measure the tenuous atmosphere, study the composition of the surface region by region, and refine the magnetic measurements that first revealed the ocean, sharpening the blurry certainties we have into precise ones. Each flyby is a fresh chance to convert a guess into a measurement. It is worth being clear about what Clipper is and is not designed to do. It is not a life detection mission. It will not land, will not drill, will not scoop up ocean water and search it for living cells. Its goal is more modest and more foundational, to determine whether Europa truly has the conditions for life, to map the ice and the chemistry and the structure well enough that we finally understand the Moon as a system. It is meant to answer whether Europa is habitable, not whether it is inhabited. Those are different questions, and the second one waits for missions not yet built. Even so, what Clipper learns will shape everything that comes after. If it confirms a thin shell in places, a chemically rich surface, signs of exchange with the ocean, then the case for a future mission that does look for life. Perhaps a lander, perhaps something that reaches the sea, becomes far stronger. Clipper is the scout that decides whether the deeper journey is worth taking, and it is not travelling alone in this larger effort, because another spacecraft built on the other side of the Atlantic is also crossing the solar system toward Jupiter, part of a wider turn in how we think about where oceans, and perhaps life, might be hiding. While NASA's Europa Clipper crosses the solar system, a second great spacecraft is on a similar road, built by the European Space Agency. Its name is JUICE, short for Jupiter Icy Moons Explorer, and it launched in 2023, a little ahead of Clipper. Where Clipper is focused tightly on Europa, JUICE has a broader assignment. It is headed for the Jupiter system to study 3 of the 4 Galilean moons, and its main prize is the largest of them, Ganymede, which it is planned to settle into orbit around in the mid-2030s, becoming the first spacecraft ever to orbit a moon other than our own. Ganymede is a fitting target because it too appears to hide an ocean. It is the biggest moon in the solar system, larger than the planet Mercury, and beneath its icy surface the evidence points to a vast layer of salty water, buried even deeper than Europa's sea. Callisto, the outermost Galilean moon, may hold one as well. So the picture that emerges from the Jupiter system is not of one lucky moon with a hidden ocean, but of a whole family of them, several worlds circling a single giant planet, each apparently carrying a sea beneath its shell. Widen the view further and the pattern only grows. There is Enceladus at Saturn, spraying its ocean into space. There is Titan, Saturn's largest moon, which may hold a water ocean deep inside beneath its thick, hazy atmosphere. There are hints of possible oceans or past oceans at other bodies still. What once seemed like an exotic special case, a sea inside a frozen moon, is starting to look almost ordinary in the outer solar system. Hidden oceans may be one of the more common places for liquid water to exist, far more common than warm, sunlit surfaces like Earth's. That realization quietly changes the whole search for life. For a long time, we looked for other Earths, worlds at just the right distance from a star to keep water liquid on the surface. But if oceans can persist for billions of years inside icy moons, warmed from within by the flexing grip of a giant planet, then the places worth searching multiply enormously. Around our own solar system, and by extension around countless other stars, there could be far more subsurface seas than sunlit ones. The habitable real estate of the universe may be mostly underground, sealed under ice, invisible from outside. Europa sits at the centre of this shift, the clearest and most accessible example of the type. It is close enough to study, active enough to leave clues on its surface, and now known to carry carbon from its sea. It has become the test case, the world where we will first find out in detail whether a hidden ocean can truly be a home. What we learn there will colour how we think about all the others, the ones at Saturn, the ones we cannot yet reach, and the untold number circling distant stars we will never visit. So the story that began with a single pale moon opens outward into something much larger, a new sense of where water, and perhaps life, might wait in the dark. But before we let it expand too far, it is worth coming back to where we started, back to the small cream-coloured marble beside Jupiter that Galileo Galilei first noticed in a cold winter sky. Everything we have traced, the ocean, the carbon, the strange chemistry, the spacecraft on their way, all of it hangs on that one quiet point of light, and it is worth seeing it once more with everything we now know. Go back for a moment to the beginning. A pale, cream-coloured marble hanging in the black beside Jupiter, the smoothest large surface in the solar system, one of the little sparks that Galileo Galilei drew in his notebook in 1610. From a distance it looks calm and finished, a frozen thing at rest. That is where we started, and it is worth returning to now, because the marble looks entirely different once you know what is under it. Beneath that smooth face lies a sea. A global ocean of salty water, warmed not by the distant sun but by the endless flexing grip of Jupiter, resting on a floor of rock that may glow with hydrothermal warmth. It holds more water than all the oceans of Earth combined, and it has sat there in the dark, stable and undisturbed, for something close to the entire age of the solar system. The stillness we see from outside is only the lid. The world beneath it is anything but still. And that ocean, we now have good reason to believe, is not empty of the things that matter. It carries salt, traced by Hubble in the yellowed ice of Tara Regio. It carries carbon, the element life is built from, found by the James Webb Space Telescope in that same broken ground, most likely risen from the sea itself. Its surface and its depths appear to trade material, cycling carbon upward and energy back down under the glare of Jupiter's radiation. Every ingredient on the short list for life, water, energy, and the carbon to build with seems to be present in one place, all at once. We do not know if anything lives there. That is the honest centre of the whole story, and it should stay in view. Having the ingredients is not the same as having life, and no telescope reading faint light off the ice could ever settle the question. What Webb found was not life, and no one ever claimed it was. What it found was that Europa has, as far as we can measure, what life would need. That is a smaller statement, and a truer one, and somehow it is enough to keep you looking up. Soon, the looking will get closer. Europa Clipper is crossing the solar system now, a machine the size of a basketball court, built to survive the storm and to answer the questions distance never could. In a few years it will reach the pale marble and begin to measure the ice, the chemistry, the ocean beneath, turning our careful guesses into knowledge. Whatever it finds, the moon will no longer be a distant point of light. It will be a place we have studied up close, one we understand. For now, though, it remains what it has always been to anyone looking up through a small telescope on a clear night, a faint spark beside a bright planet, easy to miss. The difference is only in what you know. That quiet light is a world with a hidden sea, and in that sea is carbon that seems to have come from the water itself, waiting in the dark under the ice. We may be looking at one of the best chances we have of learning that we're not alone, and it has been there the whole time, circling Jupiter, patient, since long before anyone thought to wonder what was underneath.